Now we are going to figure out how to calculate surface of rotation. And we're going to rotate the red curve around y or around x-axis and calculate the surface that would be created as a result of this rotation, revolving of the red curve. Okay? So we need to use the outcome from the previous video, theorem, about the arc length of the curve. So we did figure out how to calculate length of the red curve. In particular, we did figure out the formula how to calculate the length of this small piece of the curve, L. So this small piece of the curve happened to be equal to square root out of 1 plus derivative of y squared times dx. So we're going to use this outcome from the previously proved theorem. Okay? And then, as usual in calculus, we're going to try to figure out what would happen if we will work with the some kind of a small amount, small piece L, and then generalize, add up, integrate to get formula in general. So for now, we're going to rotate not the whole red curve, but just only this small piece L around, let's do y-axis first, around y-axis. So we're going to rotate the small L piece of the curve around y-axis, and the rotation will have radius of rotation, and it's green, it's visible. It's not hard to figure out what this radius is equal to. This radius is equal to the rotation around x-axis. So it means radius of rotation is parallel to x-axis. So we can measure our radius of rotation along x-axis. To be exact, r is just equal to x coordinate of this point. And we're going to consider the kind of the middle of this piece of curve. And because it's infinitely small, this piece of curve, it doesn't really matter which point to pick. So we just think this is kind of, it's in the middle of this piece of curve. Okay, so what do we have now? So this piece of curve, the red L, is being rotated around y-axis. The radius of rotation is equal to r is equal to x. And the next question is, what is circumference of rotation? So this is circular motion, radius r. What is the length of this rotation? Circumference, perimeter, if you prefer. So we know that from geometry, radius of rotation is defined. We can find the length of the circle, of the circular motion, and it's equal to 2 pi times r. That would be the length of the circular motion while we are rotating this piece L around y-axis. Okay, so then next question, what about surface of rotation? So this piece, the red piece L, while being rotated around y-axis, it will cover, it will paint some kind of surface in this space. And using imagination, we can agree, and using intuition also, that the surface of this space will be equal to the length of this piece of the red curve L times the circumference, the length of the rotation. So let's try to comprehend again. That's more about 3D imagination and intuition. So we have the formula to calculate the length of this piece of red curve L. Here it is. okay? And we did figure out the length of the circular motion. So this guy, the small l, will be rotated around y-axis. The length of this piece is defined at this point, and the length of the circular motion is equal to 2 pi r. The product of those, the length of the circular motion times the length of this piece of the curve, will give us the area, the surface of rotation, the area of the surface of rotation. So the surface of rotation area is equal to 2 pi r times L. And this is just a piece of the surface while we are rotating this small piece of the curve L. What if we need to figure out the surface area while rotating a big curve, like from 0, for example, to 6, this piece of the curve, or any piece of the curve? Then what? Then we need to add up all the pieces of all the surfaces. And if this is the small piece of the surface, we need to add up. And adding up in calculus 2 means what? It means integration. So we need to apply integral to this expression to find out the whole area, the whole surface area of rotation. Okay? What now? Now we need to plug in all the values. What is green R? This is X. What is red L? We have the formula. That's the outcome from the previous theorem regarding arc length. Okay, let's plug in all the values. R is X, L is square root times dx, and everything under integral sign. Plug in everything. Okay, doesn't seem to be fit. Let's try to fix it. Now it's better. So that is the outcome. So the area, the surface, of rotation, or area of the surface of rotation, while we're rotating the red curve, not just one small piece of it, but a big piece of the curve, the real curve. When we rotate it, let's say from A to B, X is changing from A to B, from 0, for example, to 6. That's the piece, the red curve from 0, X from 0 to 6, and we rotate it around y-axis. How to calculate surface of rotation, area of the surface of rotation? It's not easy even to imagine this surface of rotation, but we were able to calculate it exactly. That is the formula. Okay, so that was rotation about y-axis. Okay, so now let's do the same for the case when we need to rotate the same piece of the curve, the same curve around x-axis. What will happen and what is the difference? Rotation around x-axis. So let's go blue. If this piece of the curve, the small piece, small l, is being rotated around x-axis, the radius will be blue. And it's also easy to figure out what this blue r is equal to. It's parallel to y-axis, so we can figure out the length by measuring this length along y-axis. To be exact, the blue r, radius of rotation in this case, it is equal to y. It's equal to y. Okay, and then we're gonna follow the same logic as we did before. So the radius of rotation around x-axis now, around horizontal axis. it's a flat picture, but we need to use imagination because we work actually we are actually in 3D space. Okay, so this piece of red curve, small l, is being rotated around the x-axis. Radius of rotation is happen to be equal to y. And the question is, what is the length of the rotation, circumference of rotation? 2 pi r, 2 pi times r. The r is blue this time, which is equal to y, okay? So the length of the rotation is 2 pi times r. And next question, what is the surface of rotation when we rotate this just one small piece of the red curve L? And the same logic, the surface, the area of the surface of rotation will be equal to the length of rotation, circumference of rotation, times length of the red piece L, which is given by applying proved previously theorem about arc length. Okay, so again, this is, one more time, this is length of rotation, circumference of rotation, times the length of the piece of the curve, that, which is L, that will give us area of the surface of rotation. Area of the surface of rotation, which surface? Not the whole surface, but the surface that this small piece, small l, will cover, will paint in 3D space. Okay? And then, again, we're doing calculus 2. We need to add up all these pieces of all these areas, and all these surfaces of rotation, because we're going to rotate not just only this small piece, but a bigger curve, like from A to B, from 0x, from 0 to 6, for example. This curve, x from 0 up to 6, or any other in any other interval along x-axis. So we want to be able to calculate the surface of rotation while we rotate any curve and in any interval x from A to B. Okay, so this is the surface area, the surface just only a result from rotating this small piece. So we need to add up all of them, all these surfaces. How to add up? Integrate, because integral by the definition is Riemann sum of the pieces. So we need to apply integration. And that's the way to get the whole surface of rotation, while this red curve, any piece of the red curve, bigger piece of the red curve, is being rotated around horizontal x-axis. So that's the formula. We need to be exact. Let's plug in all the values. What is blue r? It's equal to y. What is red L? It's given right here. So this formula comes from the previously proved theorem. Okay, let's plug in everything. We're going to get integral 2 pi r is equal to y, and L is equal to the square root. Plug in everything. And here's the outcome. What's A and B? Those are arbitrary limits of integration, arbitrary interval along x-axis. For example, from 0 to 6, or from -1 to 4. Any interval accordingly. If we consider interval from -1 to 4, then the red curve will be from x -4 up to x, from x -1 up to x +4. So this piece of the red curve will be rotated, and we plug in these values into this formula and all the given function and calculate according to this sophisticated algorithm, and we'll get exact answer for the surface of rotation. So that was rotation about x-axis. So we have proved and derived two formulas how to calculate area of the surface of rotation. When we rotate an arbitrary curve, a function, it must be given like y is equal to f of x function. And it might be rotated around a y-axis, and that's the way to calculate the surface of rotation, the area of the surface. It might be rotated, the same red curve, around around x-axis, and then that's the formula to apply. So surface of rotation theorem has been proved.